Welcome everybody for coming. In today's meeting, we have Ms. Kara Reedy. She's going to give us a presentation. She is a graduate student in the Cognitive Science Department. She'll hopefully give us some insight into deep learning, neural networks, demystify the big buzzwords going around in computer science. So take it away, Kara.
All right, hello everybody. As you said, I'm going to be giving you an introduction to neural networks and to deep learning today. But this is, to start off with, this is the biologically inspired computing seminar, right? So I think to really understand how these things work and why they work the way they do, we need to understand some of the biology that inspired them. In particular, I want to start off with talking about how the brain is not a computer, but why we want to make computers that are more like brains. Now, this is a metaphor that I'm sure you've seen a lot, whether it be in news articles about new developments in neural networks and deep learning, or if you're reading books about these kinds of things. People really love to compare brains and computers. Now, part of this, I think, is because computers are the most complicated thing that most of us interact with on a daily basis and kind of understand. I'm sure that if we had this kind of neuroscience that we have today, but lived a few hundred years ago, we would be comparing it to clockwork or steamworks or whatever. Although there is actually some merit to this metaphor because there are some similarities between brains and computers that you don't see with clockwork and steamworks. For example, both of these are information processing units. I mean, that's their most basic function. Both of these have memory storage, although the nature of this memory is quite different between the brain and the computer. And both of them have parallel processing. But again, the nature of this is very different between the brain and the computer. And there's also a lot of differences, and I found that this sometimes trips people up if they're coming at it from a computer science side and not from a I took neuroscience 101 kind of side. For example, computers are digital. That is to say, at their most basic level, everything is either a 0 or a 1, right? But brains, oddly enough, are both digital and analog, and I'm going to get into this in a little bit because it's actually important for some of these models. In computers, you have memory storage as these nice files. They're delineated, they're separate from each other. You can chunk a bunch of them in a folder and organize them however you want. But memory, at least long-term memory in the brain, is done quite differently. Instead of having these nice delineated chunks, you have what are called patterns of activation. This means that the memory of your grandma's face or your 6th birthday party isn't encoded in a single neuron. It's actually encoded in patterns of activation between many neurons, let's say 1,000, and the connections between those neurons. Now, this has a really nice feature is that something happens to one of those neurons. If it gets damaged or it dies or it just forgets what it's supposed to be doing, then you have the other 999 neurons there and the connections between them, and your memory will be almost entirely intact still. Whereas if you have a computer file and you corrupt the wrong parts of it or you corrupt too much of it, you end up with an unreadable mess. So this is something that it would be nice if we could replicate in our computers. Brains are also much more energy efficient than computers. Your brain is using about 20 watts of power, and that's not a lot considering all the stuff it has to do. For comparison, this laptop probably peaks at about 60 watts of power, and it can't do half the things that my brain can do, or probably even a tenth. And this is another thing that we would really like to be able to use for our hardware. Imagine what we could do if we didn't need to use such huge amounts of energy to power our search engines, or what we could do if we had a tiny little device that used barely any power but could do some really powerful calculations. Brains, unlike computers, are very famously plastic. This means, for one thing, that they're able to learn and to change over time. But it also means that if it gets damaged in some way, it's often able to recover a large part of its function. I'm sure we've all heard of somebody having a stroke or having some other kind of brain damage, going to therapy, and maybe not getting back to 100%, but certainly recovering a large part of that function, or at least some of it. To give you a really extreme example, to show just how ridiculously plastic our brains are, especially as children, in children who have very severe seizure disorders, where they have severe and frequent seizures that aren't controllable by medication or other means, there's a surgical procedure known as a hemispherectomy. That literally means you take out half of their brain. And it sounds horrible, I'm sure, but with enough therapy, if you do it in somebody who's young enough, they're able to relearn how to walk, how to talk, and basically become normal again. Now imagine opening up your laptop and cutting out half of your hard drive and half of all of your memory sticks. Good luck with that. Computers have this nice sharp delineation between what is hardware and what is software. If you don't like what your computer is doing, you can put another program on it. But brains don't work like this. I almost find it hard to describe how badly this part of the metaphor fits with the brain. For one thing, function and form in the brain are often correlated with each other. So there are some neurons that only do one kind of thing. There's neurons that only receive information about light in your retina, for example. And these neurons look different or use different chemicals to communicate with each other than other neurons in the brain that do other things. And another thing that we would really like to be able to do with our computers is to have them teach themselves. If you want a computer to do anything, first of all, you have to program it. Second of all, it's not going to get any better at what you've programmed it to do unless you program it to do that thing better. You can throw a statistical package on your computer and have it run continuously for 10 years, and at the end of those 10 years, it'll be running that package exactly the same. Whereas in the brain, not only are we able to learn from examples in our environment and through explicit teaching, but we also become better at things the more often we do them. And it would really save us a lot of time and effort if we could make a thing on a computer that's able to learn like this, right? So these are some basic similarities and differences between brains and computers. And now we're going to learn about neurons so that we can understand how artificial neurons function in artificial neural networks. So here we have a happy little neuron. This happy little neuron has a lot of friends. And this is important because the connectivity between neurons leads to one of their most important features. Neurons communicate with each other in a way that's unlike any other cell in your body. They communicate more often and more quickly than any other cells. Of course, other cells have to communicate with each other to have your body function on a daily basis, but not with electricity like neurons do, and not in such huge numbers. Now, I said this neuron has a lot of neuron friends, and I mean a lot of neuron friends. The current estimate is that you have about 86 billion neurons in your brain, which is a lot, but also about 100 trillion connections between those neurons in your brain. And if you do the math, that's more than 1,000 connections per neuron. Now, of course, this number is going to vary from part of the brain to part of the brain and individual neuron to individual neuron. Some sensory neurons might only connect to a few other neurons, but in other areas, your neurons might be connecting to tens of thousands of other neurons. So this neuron probably has at least 1,000 neuron buddies. And when it talks with them, everything starts up here. This part of the neuron, these weird spiky bits on the top of it, are called the dendrites. They're essentially the input to the neuron. This neuron will use these to receive messages from other neurons that it's connected to. And these messages can be inhibitory, come on, calm down, stop that, or they can be excitatory, go, go, go. And these dendrites do what's called integrating all of these messages to decide what it's going to do. And the way that it does this is that each bit of the dendrite that's connected to another neuron is going to be receiving chemical messengers from that other neuron. And depending on what those chemicals are, then the dendrites will actually change the charge in the neuron. Now, usually they're sitting at about minus 70 millivolts when they're at rest. If it receives an inhibitory message, then that voltage is actually going to go down. If it receives an excitatory message, that voltage is slowly going to go up. This part here in the middle is called the soma. It's basically like any other cell if you remember your high school biology. But for our purposes, the only important thing about it is that it takes those changes in charge that those dendrites are making and moves it to this part of the neuron called the axon, this nice long winding tail that neurons have. Now, if the top of this axon reaches a certain threshold value, about minus 55 millivolts, then it does what's called an action potential. And there's something really, really important here. You either have an action potential happen or you don't have one. You cannot have a large action potential or a small action potential or half of an action potential. An action potential happens the same way each and every time it happens. And this is where the digital part of the brain, being digital and analog, comes in. When an action potential happens, what the axon does is that it propagates a charge down this whole tail here. The charge of the neuron actually swings up into being positive, has this nice peak, which we call a spike or an action potential, and then it drops down back to normal again. And when that charge that's being propagated down the axon reaches this part, this is where the output of the neuron happens. This part here is called the terminal buttons, and these terminal buttons are sitting very, very close to the dendrites of all of its output neuron buddies. And when the action potential reaches these terminal buttons, it releases chemicals. And these chemicals will float across that tiny gap between these terminal buttons and the dendrites of its neuron buddies. And this gap, by the way, is called the synapse, which is a term you'll probably hear if you do some reading on True North. And when it bumps into those dendrites, the same thing happens. It either gives an inhibitory message or an excitatory message. And this process is very quick. It only lasts a few dozens of milliseconds. And in this way, information can be thrown across to your brain in only a few hundred milliseconds. And there's another important feature of neurons that I should explain here. And that's that neurons that fire together wire together, as the famous saying goes. That is to say, if a neuron is constantly communicating with one of its buddy neurons, then they can actually change themselves physically over time to become more sensitive to the messages from that neuron. So it doesn't need as much excitation to go, oh, this neuron is telling me I should go, I should definitely go, or so on and so forth. Now, I mentioned that brains are both digital and analog. The digital part is the action potential, which you can see a graph here. But the analog part is actually pretty interesting, because information is not just encoded in these spikes or action potentials. It's also encoded in the frequency of these spikes, and can even be encoded in the precise timing in between these spikes. To give you a concrete example, when you're listening to a sound, in your inner ear, there are these tiny hairs that vibrate only when they are exposed to a certain frequency of sound, a certain pitch. And there's neurons connected to these tiny hairs And when that tiny hair vibrates, there's an action potential and you hear that pitch. But how do we get volume? Well, volume happens when that hair cell vibrates more and the neuron puts out more action potentials in a smaller space of time. The louder the sound, the more action potentials. So that's how, from one neuron, you can get both the pitch and the volume of any sound. So this was a very, very simplified version of how one kind of neuron does one kind of communication, but this is all that you really need to know to understand where we're coming from when we start looking at artificial neural networks. So let's jump into the more technically exciting part here. The basic unit of an artificial neural network has several names. It's usually called a node or a unit. It's also sometimes called a neuron. I'm going to stick with node for this talk. And this blue circle here represents one node in a network. Now, the input to any of these nodes can either be the raw data input that you're showing the network, or it can receive input that is the output of another node. And when it is connected to another node like that, the connection between them has a weight. And this is kind of the equivalent of when these that they don't have so much to say to each other and the connection weakens. This weight essentially represents how much attention we're going to pay to the input from that specific node. What one of these nodes does then is that for each input, it multiplies the input from that node by the weight between it and that input node, and then it sums all of these up together. So for this example node here, the total input would equal whatever the output of input A is times weight 0 plus whatever the output of input B is times weight 1. And then it does some kind of function on this weighted sum of inputs to obtain its output. Now, there's a lot of different functions that this node can have. The simplest would be the identity function, where it just puts out the weighted sum of inputs, but there's a lot of other ones that it can use. Now, of course, we don't typically just use a single node in isolation. You can't do very much with that. Usually what we do is that when we have all of these nodes, we arrange them in what are called layers. And a layer is a bunch of nodes that is related to its input and output layers in the same way. And they also have the same function. And when all of these nodes are getting their input from whatever the input to the network as a whole is, we call that the input layer. When their output is the output for the network as a whole, we call that the output layer. And if they're neither an input or an output layer, we call that a hidden layer for whatever reason. Now, the very first artificial neural networks kind of copied this idea of using action potentials, where your inputs and outputs would be either a 0 or 1. But the most common kind of network that's used today actually has continuous outputs, so a floating point number as the inputs and outputs. And this kind of model that you see here is called a feed-forward network because information can only move from the input towards the output, and you can't have any recursive loops in there. That is a different kind of network. So there are three, sorry?
So off that point earlier that you said where the axons kind of do the same thing every time. So why model it using floating point number as opposed to that digital?
Part of it, I think, is that with a lot of types of data, it's easier to encode things in terms of floating point numbers. For example, if you're trying to do image interpretation and you want to know the color value or the grayscale luminance value of a certain pixel to feed that into the network, you could reduce it all to binary numbers, but you might want that kind of precision. And also, this is kind of a common theme in all biologically inspired computing and robotics. Just because nature does it one way doesn't necessarily mean we have to do it the way that nature did, if it's easier for us or more interesting for us to do it a different way. Yes?
So another consideration, I suppose, you go back to what you said earlier about frequency. If you have no recurrent connections, you don't really have a concept of frequency, right? So I guess if you have floating point outputs in that, you can kind of make up for that, because you can have floating point can serve the function of frequency, you might have a real number.
Yes, we actually can use recurrency in a network that uses floating point numbers, but that's a little bit different, and I'm going to talk about those later on. But yes, that's a good point. Okay, now there are 3 learning algorithms, or types of learning algorithms, that we use in feed-forward networks. And the first of these is called supervised learning. Supervised learning is when you have a training set that consists of pairs of inputs and known desired outputs. For example, if you were doing image classification, this could be a set of input images and then a set of labels that describe what's in the image. And with these networks, what you do is you feed them your inputs and you look at the outputs and use an algorithm called backpropagation that calculates the amount of error or costs or whatever you want to call it that the network output has, and tries to change the weights so that the amount of error goes down. And hopefully the network is learning what you want it to learn. These networks are usually used for things like when you want to fit a network to a specific function, or as I said, when you want to do pattern recognition. Now you might suppose if we have supervised learning, that must mean we also have unsupervised learning, and we do. In unsupervised learning, you don't have this set of known and desired outputs. You only have inputs. And you have a function that describes how you want your network to relate its inputs and its outputs. The most common example of this would be that the input and the output should be equal to each other. And these kinds of networks are often used, when you're trying to do clustering, when you have a group of things and you want to know how should I group these based on their different properties. And the third type, my personal favorite, is called reinforcement learning. In reinforcement learning, you don't just have a network, you also have an environment of some kind. And your network is going to be getting its inputs directly from whatever its sensors are in this environment. So one example of an environment is having a robot in some kind of learning tasks. And in that case, your input could be whatever sensors are in the robot. Or another common example of reinforcement learning is if you want to teach your neural network to play a game. Let's say you want your network to learn how to play checkers. In this case, your environment is going to be the checkers board, and your sensors are going to be the positions of the pieces. Then your network does what it does, and its output is used as an action in the environment. And you also have a reward function that is going to give your network a reward depending on how well it does at what it's supposed to do, or how the environment is changing. And these don't have to be necessarily close in time. For example, if you're trying to teach your network to play checkers, then your reward is going to be 1 if you win the game, -1 if you lose, and probably 0 if you draw. And your algorithm can then go back and change the weights to try and make it more likely to get that reward next time. It essentially tries to maximize the reward. And this was used, for example, does everybody remember when Google suddenly beat Go a couple of months ago? Well, one of the tools that they used was reinforcement learning. Not only did they feed this network a bunch of different Go games, but they also had it play against itself in this kind of reinforcement learning environment to have it improve over time. So I mentioned that you can have networks that loop back on themselves. Well, these are their own special type of network called a recurrent network. And they have their own different learning algorithms to cope with the fact that you have this recurrence. And these are often used for things like natural language processing, when you need to remember what word you saw before the word that you're looking at now, and so on. So these are the most common types of networks that we see today. There is also another kind called a spiking network, which is a newer kind of network that harkens back to this concept of using action potentials to do information encoding. So these spiking networks take even more inspiration from biology and try to encode more biological features in how they work. And there's actually a whole bunch of different models, some of which have more or less implementation costs, some of which have more or fewer biological features. I believe the most popular one right now is called the Iskovich model, which actually does pretty good on both implementation costs and biological features. And this kind of network is also used in neuromorphic computing hardware, such as the True North chip. If you have a network and you want to put it on the True North chip to gain the advantages of doing so, having it work more quickly and much more energy efficiently, then you have to figure out how are you going to encode your information in terms of action potential spikes. All right, now on to deep learning. Deep learning means that there's a bunch of layers, essentially. So normally in a feed-forward network, you don't have more than one or two of those hidden layers. And part of this is because it's expensive to train a bunch of hidden layers, especially if those layers get very large. And part of this is because we just didn't have the computing power to do that very often in the past. But now we have better computers than we had even a decade ago. And we also have new techniques to reduce the training cost of these deep networks. And this means that we now have networks that can have dozens of layers or even over 100, which means that we have a lot more possibilities opened up to us. People have had some really good results using these to do tasks like object recognition, handwriting recognition, some natural language tasks. For example, Google's Go program used deep learning, and in particular convolutional networks, which I'm going to walk us through, in order to achieve its high Go playing abilities. Okay, let's say that we want to be doing some kind of image processing on 8x8 pixel images. Maybe we're just trying to learn how to recognize handwritten numbers. Very simple task, right? It'd be nice if we could use something from our own visual processing system and from the spatial dynamics of these images in order to process them better. So a convolutional network starts with one input layer. And in this input layer, each of these nodes corresponds to one pixel in our source image. And then we have a hidden layer. In this hidden layer, each node represents some small spatial part of that input layer. In this example, it's 4 pixels that are next to each other, but you could also do a 3 square or a 4 square or whatever you want to do for your hidden layer. And each of these nodes in the hidden layer is also going to account for a slightly different part of the input layer. So you can see that the first one in our hidden layer represents the 4 pixels in the top left, and then the second one represents 4 pixels shifted 1 over. And we do that for the entire image. And this is called a convolution, which is why these are called convolutional networks. And there's something very important here. All of those weights from the input layer to this hidden layer, they're all the same. They share the same weight. And this is because what we're trying to do here is we're trying to learn how to recognize features in the image. And we want to be able to recognize those features no matter where they are in the image. Like if you're trying to learn how to recognize cats in random internet pictures, then you want to be able to recognize it as a cat, even if it's on the left side of the picture or the right side of the picture or the middle of the picture or wherever it is in your image. So essentially, this entire hidden layer is trying to learn one feature wherever it is in the image. Now, maybe you're saying, but I don't want to learn one feature, I want to learn 20 features. Well, you can add 20 hidden layers, and they'll all be connected to this input layer as essentially parallel. And well, each hidden layer as a whole will have different weights. Each node within a specific hidden layer will share the same weight. And this also helps reduce the training cost by a lot. Okay, now we move from our hidden layer into something that's called a pooling layer. In the same way that the convolutional layer had a bunch of overlap when looking at the input layer, the pooling layer kind of does convolutions on this hidden layer. But there's a difference, because in the hidden layer, you're essentially trying to look at these 4 square pixels in this example. In the pooling layer, you're trying to summarize that small group of nodes. So there's different functions that you can use to do this. A common one is called softmax, where essentially you look at the activations of the different nodes that this pooling layer node is responsible for, and you output whichever one is the highest. As I said, there's a bunch of other functions that you can use for that. And then, if you really wanted to, you could then add another convolutional layer to this pooling layer, and then add a pooling layer to that convolutional layer, and then and then just keep going as far as you wanted to. In this example, though, we're going to cut it short at 1 pair of convolution and pooling. And all those 20 pooling layers for all of those 20 convolutional layers are going to output to the output layer. Or again, you have options. What you could do instead was have them connect to a normal hidden layer, not a convolutional one, and then have that hidden layer connect to an output layer, but this one's a little bit more straightforward than that. And using this technique, people have had successes in improving the accuracy of handwriting recognition, of labeling images, and doing all sorts of really cool things. So deep networks are pretty powerful, and that's why people are getting so excited and hyped up about them now that we're able to do these things. So this covers all the basics of neural networks and deep learning, but before I let you go, I need to talk to you about some advantages and disadvantages of neural networks. Because a neural network is a hammer, and you cannot go using a hammer on screws. Now, they are very nice in that they're able to be applied to black box problems, which means that if you don't know how things are relating to each other, or you don't really know where to get started, or it's a very complex issue and you just want to throw a neural network at it, you can do that. The problem is that the neural networks themselves are black boxes, which means that you might solve your problem, which is great if that's all you need to do, but you're not going to get a greater understanding of what's going on here. All you've done is solve the problem. You don't know how's the problem being solved. Another problem that kind of ties into that is that it's hard to know what the meaning of a neural network's output is. I mean, we ascribe it meaning, but to the neural network, it's all just numbers. And again, this doesn't help us understand what's really going on in this problem solving. Now, they are nice in that, as I said, they're really good for pattern recognition and other tasks, which I'm going to talk more about in just a moment. And they can also produce some surprisingly human-like results, which is great if that's what your project involves, for example, in different kinds of natural language processing. They're also relatively easy to use and implement. You might have to spend some time tweaking what are called the hyperparameters, which includes things like how quickly you're or how much you change the weights at any given point. But you can download a neural network package, download some open source data set with a few tens of thousands of files, and throw your neural network at it and achieve maybe not a perfect network, but it'll be something that looks really impressive and will make you feel like you're having a lot of fun. And they're also suitable for parallel processing, kind of in the same way that you can do parallel processing in the brain. A couple of other disadvantages is that you really need to have enough data to train your network. If you only have a small pool of data, then either you're going to have to use another machine learning technique, or you're going to have to use a very small network. Now, that might not be a problem. Adding more nodes and more layers and so on to a network doesn't necessarily improve performance depending on what you're trying to get it to do. But one guideline that I've been told is that for each parameter in your model, you want to have at least 3 pieces of data. Now, each weight in your network is one of those parameters. Now, okay, you have hundreds and hundreds of connections, weights in your network, you're going to need at least 3 times that much in terms of data. Now, say you're trying to do deep learning, and maybe you have thousands of weights in your network. You're going to need a lot of data. Going along with this training, especially if your network gets very large, it can take a really long time. Now, there are ways to reduce this, first of all, by using a smaller network. And also, sometimes you can use your GPU to do training of the network instead of using your CPU. But it's still going to take a while, so if you're impatient, neural networks may not be the thing for you. And that also means that it can be a bit harder to do a lot of experimentation. If you have this huge network and it's taking you a week to train on your crappy GPU, then maybe you don't want to be doing tweaks to it every few days. And one last thing that really frustrated me when I was trying to learn how to do neural networks is that there's not a lot of hard guidelines on what makes a good neural network structure for any given problem. Now, if you're trying to do something similar to what somebody else did, you can go look at their data and see what kind of network they used and try a variation of that. But if you can't do that, then you're going to have to make stuff up, because nobody really knows how these things work. They're black boxes. We put numbers into them and numbers come out. So if you like doing experimentation and trying different structures, and you won't be disappointed if it doesn't work the first dozen times, that's great. If you want really hard guidelines of, if you're doing this kind of task, then you don't want more than this many hidden layers, and the weights should start in this kind of range, and you should have this many hidden nodes for your input nodes. There's nothing like that. So if that kind of thing is going to frustrate you, again, maybe neural networks are not for you. Now, as I said, you can use neural networks to do image recognition, game playing, natural language processing, but there's other things that you can do with them if these things don't appeal to you. For example, I've seen an example of somebody using a neural network to make music. They fed a network a bunch of guitar taps, and then they uploaded a recording of what the network produced. Now, it wasn't great music or anything, but it was probably better than what I would have produced if you handed me a guitar. And, of course, if you are trying to do something a little bit more biological, if you are interested in artificial life, then neural networks are a great place to start. And actually, I'm going to show an example of my own research project involving neural networks and artificial life. So this is my artificial life simulation. I don't know how well you can really see it on the screen. But this uses that reinforcement learning that I was talking about earlier. This is my environment. I call it a garden. You can see it has plants in it that the creatures can eat. It has these balls that they can play with. There's a rock in the corner here that you can't see on the screen at all, but it's kind of an obstacle for them because it's not fun to play with, and also it really hurts if they try to eat it. All of these blue things running around are the creatures. Each creature is powered by a neural network that uses that reinforcement learning to learn from its actions in the environment over time. In this case, the input is what it can see right in front of it, and also its own internal sense of things like how hungry it is, how bored it's getting, if it's in pain or not. And it also has a kind of short-term memory for what actions it's carried out previously. And the output of this network is the action that the creature is going to take in the environment. Is it going to try and eat what's in front of it? Is it going to try and play with what's in front of it? Or is it going to turn around and go somewhere else? And yes, they can interact with each other. No, they're not allowed to eat each other. And in this case, the reward is how well they fulfill their own needs. If they do something that fills their hunger up and keeps them from starving to death for a little longer, then that's rewarded. If they do something interesting to them, that's rewarded. If they try to eat a rock and they cause themselves a lot of pain, that's punished. And the goal of this project is to have these little critters learn how to have long and hopefully happy lives in this environment. You also don't have to use neural networks in isolation. You can combine them with other machine learning techniques. For example, Google's Go program used tree search techniques when it was trying to figure out what moves it can make or should make. And in my case, what I'm doing is I'm implementing a genetic structure that will describe the topology of these networks that the creatures use, and they'll be able to evolve over time. And there's actually a lot of literature out there on combining neural networks with genetic algorithms, if that's something that sounds interesting to you. Well, that's all I have to say for right now, but any questions? Yes?
How big is your network?
How big is my network? Let's see. It's very small, actually. I think I've got 13 input nodes, 5 action nodes, and then a few others that are basically needed to make it work with the neural network package that I'm using, which is called Caffe. And hopefully in the future, because it's written in Caffe, I should be able to move it onto that true north strip and see if something blows up. Yes?
So you mentioned there are no sort of hard rules as to how you're going to structure your neural network. And so for your project, did you kind of experience any of that frustration of not really knowing what structure I should have? And how did you go about improving it? Because since it's a black box, you don't really know what it's doing. How do you know which direction to take in order to improve your?
That is a very good question. So in my case, I started off with just hooking up the inputs to the outputs. I didn't even have the short-term memory at that point, which is something that I added later. Now, this might be improved if I added a hidden layer. I haven't tried that because I'm currently working on the genetic structure, but maybe it would do something good. In my case, what I tried to do was I looked at other artificial life programs. The biggest inspiration was something called Creatures, which some of you might have played many, many years ago. And I looked at what Creatures is doing with its neural networks, which are much more complicated and larger than mine. So I took a little bit of guidance from that. Otherwise, it's mostly experimenting with your network and seeing if you get a different result. So if you have a hidden layer, then if you add more nodes to it, does your accuracy improve or does it not improve? And if it doesn't improve, you can go ahead and take those out because you don't need to bother training those. Does adding another hidden layer improve anything, or does it just increase your training time? So that's the biggest thing, I think, is it is just trying to see what have other people done before, if you can, and just literally just trying different things. Yes.
Through your research, have you found anything that where anyone documented like what a lot of data is, like possibly for image processing? Like would a lot of data for one object be 25 images, or would that be 250 images?
We're getting into thousands, tens of thousands.
So I don't know of any specific documentation source like that. I only have the guideline that was given to me verbally by a statistician. It's possible that might be out there somewhere. I haven't done that sort of work before, so I haven't gone specifically looking for it. As you said, we are up into the tens of thousands of images stage. For example, there's this data set called MNIST, which is a collection of handwritten digits, and that has 60,000 images in its training set. So yeah, with images, because we have a lot more storage nowadays, and because it's easier to scrape things off Google Images or Flickr or whatever, it's pretty high. And I know for natural language processing, I've seen it in the millions of characters. So sorry, I can't help you further.
So to answer that question, there are actually theoretical bounds on the number of images that you need to obtain a certain a minimal gap between your in-sample area and your out-sample area. Those bounds are often gross overestimates of how much training data you need, and then there are like sort of empirical rules of thumb that are talked about in the literature that you can use to give you a better idea of how much data you need. But there are some hard and fast rules for how much data is theoretically required to obtain good results.
Yes.
So kind of going off of the topic of like how much data do you need to actually train? Is it actually possible to sort of like overtrain a network?
Yes. That is actually a big problem, that if you look at any how to do neural networks guide, it'll give you more details about how to avoid overtraining. The statistician who told me that thing about 3 points of data for every parameter, he actually got really mad when I asked him about neural networks, because his experience with them was in the early 90s when people had discovered this wonderful new machine learning technique and they were throwing lots of data at it and they were getting all of this crippling overtraining. And they're like, oh no, how do we fix it? And the statisticians had already been working on models for a really long time, and they already had guidelines for avoiding doing that. So yes, you can overtrain or overfit your network, and if you want to be doing anything with them, you should read up on how to avoid doing that.
Sorry, just to add on to that, to avoid confusion, more data means that you're less likely to overtrain. So the fewer data points that you have, the more likely you are to overfit to those data points and essentially have your network memorize the answers for whatever task you're trying to perform. So that's basically one of the big reasons that you need a lot of data for training neural networks, because they're very prone to overfitting. And there's other ways besides just getting the data to avoid overfitting.
Any other questions? Yes.
So I guess going back to the example that you gave of feature detection in that basic feed-forward neural network. So I know you said it was kind of like a black box. Right? What exactly does a feature look like once it's in the network?
You mean in the convolutional network? Or
Yeah.
okay, so that's a good question. And it's also something that we don't super know the answer to. When you can kind of run the network backwards and see what it's learned, if you do that with a convolutional network, then you kind of get what look like small shapes or like lines of different orientation. So people suppose that just as our own visual system is good at detecting these very small features, we have neurons that are sensitive to lines of very specific orientations in our occipital region. So people suppose that it's maybe working like that, but we're not 100% on that, especially because if you take these networks and try to find images that trick them, it's not that hard to find an image that doesn't look like anything to a human eyes, but the network will be, oh yeah, that's definitely a cat, 100% cat. So black box problem again.
Anyone else?
Yes.
Just to add on to that, real neurons behave the same. Professor of neuroscience at Emory a while back.
I'm sorry, could you speak up a little bit? I can
Yeah,
barely hear you.
the scientist guy at Emory did experiments on lobster brains, and by stimulating different parts of the brains that were completely unrelated to eating, they could stimulate it and create or activate the feeding behavior of the lobster. So it's even the real stuff is all black box too. Right?
Yeah, we're still trying to figure out what's even going on in there. Yes.
So if it is so black box, when you're designing the neural networks and all the different layers for a convolutional network, is it a lot of trial and error, or are there any techniques that you guys use to? I guess go ahead. That's probably
Yeah. So the basic structure of the convolutional network, I think, is fairly straightforward. You just have, again, you kind of have these different options that you can try, although depending on how fast you're able to train them, you might not want to do too much experimentation. But you can have convolutions of different sizes. You don't even need the same convolutional size for all of your different convolutional layers. You could try adding a hidden layer before your output layer, as I mentioned. You can try doing different adding more convolution and pooling pairs if you think that might work. But if you're getting I think what people usually do, from what I've read, is that they'll try the kind of straightforward one convolution, one pooling in 20 different layers maybe, and then your output, and see what kind of accuracy you get. And then maybe try some other stuff to see if you can improve that if it's not very high. But that basic structure that I showed, something like that can get over 99% accuracy on trying to recognize handwritten digits. And I've seen what it classifies wrongly, and some of those would be really hard even for a human to classify correctly. Now, maybe if you're trying to do something more advanced, like you're trying to show it pictures of animals and say, that one's a fox, that one's a wolf, that one's a cat, that one's a frog, that one's a turtle, then you might need more of those layers. But I think usually it's see what your baseline is with something simple, and then see what helps when you try to complicate it. Or if you don't need to complicate it, then you're good.
Thank you, Kara.
Yes.
Especially when I get back and see how it did.
Fingers crossed. Nice job.
Thank you.
Yes. Yes, so we're gonna have
Yeah, whether you just ship it. Yep.
right now we're thinking of Paris.
Hey, my ribs don't hurt. Thanks.
Any options?
Good job. Ich weiß, wie rum ich das
I think that these chairs can go all the way up to the
get more so.
Those are just like hurts me.
What's great is
Being like brain your chair. It's like it doesn't go all the way.
Ramped up the difficulty really well. You ramped up the difficulty really well. I thought your pacing was excellent. Like for real,
I succeeded, yes.
you started out, I'm like, wow, this is really basic, and you got into like stuff I've not really read, so it was like this one. It's excellent.
I guess all that experience with trying to explain what my program is to other people is paying off.
See, and eventually you can turn that into being a professor. It's just the same
I don't want to be a
exact
professor, I want to do research.
Oh,
But
yeah.
Not actually, I don't feel like I'm good at teaching. My throat gets sore too easily. Maybe I might get stuck in it, but
It's stuck in.
we'll
If
see.
you don't want to do it,
We'll see if anybody wants to hire me to do something else other than
please.
people.
Bet you can find something. Computational neuroscience is a hot field. It's ridiculous.
But will people pay me to do A-Life? But will people pay me to do A-Life?
I don't know. That's a good point.
I mean, Creatures
Mm-hmm.
was a game that happened in the virtual life in the late 90s. But I don't think there's anything like that that's in existence. Maybe the market is crying out.
Make it like just rename your bugs to like I don't know, insurgents, and so it's to the military intelligence community.
I think it had a few more features. So should I turn the cannibalism off? Should I turn the cannibalism off?
Yes, but with a very, very high penalty. I'm gonna go clean up my laptop.
We have some documentations that.
Thank you.
I succeeded in teaching people how to think.
You did. Yeah, I understood. It was a very good overview. I'm finally ready. My brain is all the arts stuff to do. Is anybody even doing anything?
So it might be.
Black box.
How long have you been doing
Black box. Just teach them all that how to do philosophy. They'll definitely know black box.
Kara, are you a black box? Is that where?
We're all black boxes in our house.
It hurts training us skills. Cherries.
I remember counting ID within that.
Yeah.
Still pretty early.
It's a good lyric for punk rock.
So yeah, it's like, so I.
Maybe I should just run all over the question.
We'll stop on our
People get
presentation.
tired because they also have too many around.
The next one will be about-
Right now, we
So whoa.
And it's, they're like, we're gonna get like 90%, so we have to be.
What happens when spring happens? 7, 6, 7, 8.